Okay, thank you very much. Good morning, everyone. Can you hear me, especially those at the back? Could you see my handwriting? Yeah, perfect. Okay. Well, thank you very much for coming, and welcome to the second week. I'm also one of the organizers of the school, and of course, you can welcome to goes without saying. You can ask me any question, both in during the lecture Q&A, and I'm will be around the whole week this week. So yeah, and this course will be about anomalies of the Hooft and Adler-Projective type. This course also serves as introductory course to the generalized global symmetry by Michele Del Sotto. He will come tomorrow afternoon, and so this is an essential part that probably he will use some or a lot of material in this course. So yeah, serve as an introductory course, and some part of it will be more contemporary, some part of it will be more vintage. Okay, so what is this about? I should mention there is a lecture note online. You can go by this link. If you don't want to take a note, feel free, because it contains everything I would say. It's very systematic here. You can even read it. What I'm saying here will be contained in the note. The note will be constantly updated, because when you have question and if some point are not clear, I will update the note. Okay, so check it daily. Okay, so what are we talking about? So we will study system with an internal global symmetry, G. So meaning that, okay, you can find Lagrangian description, Hamiltonian description, or whatever, and there's some symmetry that left it invariant. Okay, it's global symmetry. There will be a lot of example after. If you find this a bit more abstract, just bear with me a second. It's just introductory to the subject, and you can couple G to a classical background gauge field, which I call A. Okay. So what is classical background gauge field? It's like if you have a system, think of it as a quantum mechanical system, you can couple it to external electromagnetic field, external magnetic field, for example, external electric field, for example. This is classical background field, okay? You can, when you have a background field, you can turn it on or turn it off as you wish. You can tune it to be very strong, very weak as you wish, okay? This is concept of classical background field, okay? It's an external field that you use to probe the system. This is very important to have this thing, okay? You will see. Some phenomena that we talk in this lecture, you will not see it at all if you don't turn it on, but you will see it when you turn it on, okay? This is a characteristic of this thing. Then you can place it on a closed Euclidean manifold and compute the partition function, which I will call Z as a function of A, okay? I will demonstrate this. If this is a bit too abstract, bear with me, okay? So what is the main point of this lecture? The main point of this lecture will be about Hooft anomaly. What is Hooft anomaly? It is a statement that under a gauge transformation, A goes to A to the lambda with lambda a gauge parameter. This partition function transform as z of the a to the lambda equal to z of a times some phase factor, which I will write it as 2 to the minus pi I integral alpha lambda of a, okay, of x. Okay, let's study this. Okay, what is x here? X is our space-time. A was our gauge field, okay? So, and alpha is, okay, let me stop here. So when you do gauge transformation, okay, which you can do because A is a gauge field. Any gauge field is subject to a gauge transformation, right? Like this. Partition function is not really gauge invariant. It's gauge invariant up to a phase, which is this exponential. And it's depend on this parameter alpha, which is depend on the gauge parameter and the gauge field itself. Okay? Is that clear? Whenever this happens, you say that, well, which subject to one further condition. But if this happens generically, and you cannot remove this thing easily I will define soon. This is called Hooft anomaly. Okay? This is a definition of Hooft anomaly. So let me write further. And the phase function and the phase factor cannot be removed, because if it can be removed, it's trivial, right? Yeah, it cannot be removed by introducing the so-called counter term. What is counter term? Counter term are local function, which are local function of background field A. So suppose that you compute this and you insert some local function A in the action and compute this thing, and you can remove, this is not anomaly. If you cannot remove it, it is anomaly. At this point, you might say, oh, it's so abstract. What is this? I haven't seen any real example. I will do it soon. I will start from quantum mechanics, okay? Which is everyone is happy because it's in quantum mechanics. And then we'll move on to quantum field theory, and we will see this repeatedly. And Hooft anomaly is very interesting. The subject of it is so rich because, why? I give you one definition here. But it's an animal where you look at it from different angle, it has a different looking, but it's the same thing. This is why the subject was so rich and beautiful. You will see. Okay, this is the definition that people use, and it's a definition that it's solid. Okay, persists in every system like this. Okay, so this is the background field. So I'm telling you that under gauge transformation is not really a gauge partition function is not really gauge invariant because of this phase. What's the consequence of this? If a global symmetry has a Hooft anomaly, you can make A dynamical by putting it in the integrated or in the path integral. This is the difference between background field and dynamical field. Okay, background field is something that you put externally. You can turn it on, turn it off, but you can make this background become dynamical. Dynamical means that you integrate it in the path integral. Okay, if you do that, we call this gauging. You make it dynamic. A become dynamical object. It's not just a classical probe background field anymore. So if your A has a Hooft anomaly, what happened? When you do path integral, remember you have to path integrate over everything that is gauge equivalent. A and A lambda are gauge equivalent, right? So what is this statement? When you path integrate over A and A lambda, this phase obstruct the gauging because it's not equivalent anymore, these two partition functions. If ZA and ZA lambda are equal, you can path integrate it without problem. But there is an obstruction here, which you cannot remove, right? So one consequence of Hooft anomaly is that Hooft anomaly is an obstruction to gauging. Okay, this is one consequence. There are more consequences. For example, trivial theory cannot have Hooft anomaly, but this we will talk about it later. Okay, so enough abstraction, I think. Let's do some physics. So please. Yes, this is the most general way of stating Hooft anomaly. Yes, every system will have this characteristic. Okay, but you will see several manifestations of this statement. Okay, so right, let's start with an example. So I will start with a particle on a circle. This is just a quantum mechanics. But in this system, you will see that it has a Hooft anomaly. Okay? So how come that the quantum mechanics has an anomaly? I never see this kind of thing, but okay, you will see. It's quite interesting. Okay, consider a Lagrangian. L is 1/2 mq dot square. This is a kinetic term, right? And I will add this term, theta over 2 pi q dot. Okay? Where the coordinate q is periodic. So meaning that q, I will take it to be identified with q plus 2 pi. Okay? Is that clear? Okay, let's start with this. This is just a simple Lagrangian. Okay? You might ask, what is this system? Is it real? Yes, it is. This system is a particle of mass m moving around the solenoid with magnetic flux theta. Really, if you look at the Lagrangian, it is precisely this one. So it's physical. Okay, so we put a solenoid and we let the particle moving around. Is that clear? Okay. So first thing you can observe here, Noppadol, you put the total derivative in the Lagrange. Can I drop it? So, okay, good. So indeed, theta term is a total derivative. And as you learn from your classical mechanics, quantum mechanics, this usually doesn't affect the equation of motion. But you will see that when you quantize this system, it affects the quantum behavior of the system. So we better not drop it. And you will see that it has a very, very far-reaching consequence. Okay? Good. So what do we do when we have this type of system? Oh, sorry, I can use this one. Okay, so we can compute conjugate momentum, which is pi of q. You can compute it like this, right? Which is turn out to be this one. And then the Hamiltonian is h, which is a function of theta, is pi of q dot minus L. And this, if you polish it, you will have pi of q and over, okay. And as you know in quantum mechanics, you replace conjugate momentum with the derivative, okay? So this is passage to quantum mechanics. Is I d of q minus theta over 2 pi square. This you use commutation relation, okay? Good. So we can consider time dependent Schrödinger equation. Okay, so what is this? This is just this guy minus theta over 2 pi square equal to e, sorry, this is a wave function of n equal to e n of psi n. Okay, so this is what we do. So what's next step? We look for a wave function, right, which is single value. Single value in Q. Okay, so side of n of Q is, I normalize it like this. Okay, when you plug this in, you will find the energy spectrum. Energy eigenvalue spectrum to be E of n equal to 2m n minus theta over 2 pi square. And here I take n to be any integer. Okay? Good. Can we plot this? It's just a parabola, right? Plot what? Okay, so let's plot E and n and theta. Okay. Can we try? Oh, let's take n first equal to 0. Okay, this is just theta over 2 pi square. Okay, up to it, it's just really a parabola. Approximately look like this. Okay, this is n equal to 0. Since I'm colorblind, I'm going to use white chalk, okay, because I cannot distinguish. Okay, how do we do it? So let's do n equal to 1 here. This n equal to 1. And you can see that n equal to minus 1 is approximately like this. It's very, okay, it intersect here. Okay, n equal to minus 1. Sorry for my drawing, okay, but you see what I'm trying to do. Okay. Yes, okay, this is 0. What is interesting is here. Can you see at the back my plot? At pi, there is an intersection of the two curves. Is it? You agree? Two parabola will have to intersect at some point, and there's an intersection at the pi here. This is called level crossing, meaning what? It crosses between n equal to 0, for example, and n equal to 1. Okay, this is the crossing, and this will lead to a very, very important physical consequence. Just observe this for now, okay? Next thing you should observe is that the spectrum is invariant under theta goes to theta plus 2 pi. Is it true? Yes, when you shift it, but you have to shift n also, right? But it shifts all the state. N goes to n plus 1, right? Yes, it's invariant because you can shift any integer would do, right? But you have to shift n also. Have anyone seen this phenomenon? Who studied string theory here? Who have studied? Have you seen something similar to this? This is called spectral flow. Okay, this is an example of spectral flow. So good. So already here you can see that the theta has some periodicity. Okay, so meaning that theta has a 2 pi periodicity. You can see this even more clearly. I will provide two statements where to see this thing, okay? At this point, is it clear? Okay. Or please let me know also if you feel like it's too fast, okay? And you cannot follow any argument, or I should write more and this kind of thing, okay? Good. Of theta, okay? So to see it is the first way. So I will show that the theta is really 2 pi periodic. Okay, you have seen it from the spectrum already, but if you're not satisfied, you can look it from the action. By the way, my argument here you can uplift to quantum field theory. It's the same. Those who have seen something called theta function, this is the same thing. It's just a baby version of that, but it's the same proof, okay? So let's consider, so okay, you consider Euclidean action. So now I will write down an action of this. You have used Lagrangian. Oh, by the way, so I will do everything in Euclidean signature. And if you not get used to it, there's some I that you might not get used to. But if you make the T goes to IT, you will see that it go back to whatever you get used to. The reason I do everything in Euclidean space-time is because when I compute partition function, I need to do that, first of all. And time and space are on equal footing. There is no distinguish between time and space, okay? And this is the most rigorous way of doing anomaly because there's no weak rotation I need to do. You will see this later, okay? This will not be so important in quantum mechanics, but in quantum field theory, this is rigorous, okay? Good, so let's start by doing this. So we are in quantum mechanics. We just have this, and we have I theta over 2 pi q dot. Okay. So we take a Euclidean action, and let's compactify time direction. Tau goes to, identify with tau plus beta. So roughly, I make it periodic. You can make it as large as you want. It's not so important, okay? Just pretending that we compactify it. There are a very interesting field configuration. You know, anyone can guess what I'm trying to do? This is called Instanton configuration. How many of you have seen Instanton? Perfect. If you don't see it, don't get panic. I will introduce everything here. Okay. Which uh, known as Instanton. Okay. What is it? Labeled by the winding number. Okay, we erase it. Of the map. Look at this map. The coordinate that you just write down is the function, right? Q is a function of tau, of time, right? It's a map from what? From S1, which is tau. Why is S1? Because we make it periodic by beta, okay? Is it clear? To another S1, which is S1 of Q. You remember we take Q to be 2 pi periodic. So there are two circles here. One is with the circumference, or let's approximate the radius beta, and the other is radius 2 pi. And what happened here? I don't know. We don't have rubber band here. So imagine you have a tube, okay, and you wrap a rubber band. There is some quantity called winding number, a number of times that you wrap the two circles, okay, on each other. This is this winding number. And the field configuration that we are looking at here is instanton. Is it clear? Yeah. So this is this. And how do you see this? So you just compute this. So take the S1 of tau and d tau, and then you compute this thing. You can just integrate this, and this will be 2 pi p, where p is in z, where p is known as the instanton number. Some people call this winding number, okay? So where does this come from? This comes from this piece. Okay? Yes, please. Yes, yes, it's exactly, exactly. Yes. In the Euclidean path integral, the Euclidean path integral contains e to the exponential to the minus s. You familiar with this? When you compute path, you path integrate over this quantity, okay? So what happened? You raise this to the exponential with a minus sign. So this, you have to use this, right? With the second term, okay? So it is weighted by exponential e to the theta p, right? With p integer. correct? Because 2 pi cancel and so on. Yes. We see that partition function meaning the Euclidean path integral is invariant under theta goes to theta plus 2 pi. Yes, I'm doing classical configuration here. Yeah. Integrate over what, sorry? Yes, but there is this one. And this is the one that relevant for 2 pi periodicity of theta. If you show that this exists, theta has to obey this. Otherwise, not invariant, right? You just pick. Okay. So what let's go back to our purpose here. What I'm doing here, I will show that theta has a 2 pi periodicity. You have seen already one way here from the spectrum. Here is a second way. This is how you show that there exists a few configuration. This is known as Instanton configuration. And under this configuration, to be consistent, theta has to be 2 pi periodic. Okay, that's the logic. Is it clear? You pick a configuration and you show that to be, for this configuration to be consistent, theta has to be 2 pi periodic. This is the same as in quantum field theory. When you have the, if you do quantum field theory, there will be the epsilon mu nu sigma rho f mu nu f sigma rho here, or f VHF term. This is the same argument. You pick an instanton configuration and you show that to be consistent in the path integral, theta has to be 2 pi periodic. It's the same in quantum field theory as in quantum mechanics. Okay? So this is called theta term. Okay? Good. There is a second way. Second way is very brief. I'm doing first way because we will use instanton configuration constantly in the lecture. So this is, if it's your first time, this is a good time to learn it. If you have seen this, bear with me. We will use it continually. Okay? And the P is integral because the first homotopic group of S1 is an integer. This is a underlying mathematical statement. Okay? But you have seen it in front of you here. Excellent. So the second way, okay. So we show that h theta and h theta plus 2 pi are related by a unitary transformation. Okay, so how do you show this? You just pick this thing. And you can put this in the exponential and using your Hamiltonian, which you have seen. Okay, and after some computation, put this in the derivative and cancel this. You will see that this is equal to h theta plus 2 pi. So what I'm doing here, I'm showing that h theta and h theta plus 2 pi are unitary equivalent. Okay, if two operators are related by unitary transformation, in quantum mechanics they're equivalent. Okay, so observe that I have to raise q to the exponential with the I. This is because q itself is 2 pi periodic. To make it well defined, I have to put it in exponential, and this is a good operator. Okay? Any questions so far? So this is our system. I have told you the spectrum. I have told you the property of various parameters in the theory. Next, we will talk about global symmetry of the theory. Okay? And this is where the, the, the core of the subject is going, because we want to look at the system with global symmetry. And this theory actually have two. Any question? Okay. Okay, let me keep that. Okay. Okay. So what are the symmetries of this system? There are two of them. Okay. One is you can observe immediately. Can anyone tell me what is very immediate when you have a Lagrangian of that type? You can shift Q by some parameter, right? Some constant parameter. And it's left Lagrangian invariant. You agree? If this is true, you call it global symmetry, right? Okay, good. This is a first global symmetry. I will refer to it as shift symmetry. Okay. At any value of theta, this is true, right? Because there is a U1, which, well, since as a group they are isomorphic, I will write U1 or SO2 interchangeably, okay? Which act as Q goes to Q plus alpha. Okay. So if there is this type of symmetry in quantum theory, you should be able to talk about operator that act on the Hilbert space, right? Okay, so in quantum mechanics, it corresponds to an operator, which I will call O alpha. I will put my handwriting O to emphasize this operator, okay, with the parameter alpha that act on operators and states as O alpha e to the iq O minus alpha. This is how you conjugate, right? And this is, again, the well-defined operator. You have seen what it does. It shift q by alpha, right? So you write it as e to the I alpha, e to the iq. Okay. And what about the state? If you have O alpha act on the state n, it alpha n act on n. Okay? Is it clear? Okay. This, you can see this very clearly from the Lagrangian or the Hamiltonian, right? And the second one, okay, is called parity. And some people refer to this as charge conjugation symmetry. Okay, I'll explain why. Okay. Parity or charge conjugation symmetry. This is the second global symmetry that we have. Okay. This, although exists at any value of theta, The parity or charge conjugation symmetry exists only at theta at 0 or pi, okay? Okay. I invite you to look at Lagrangian again and see if this is true. This because the pi is identified as it's periodic. The theta is periodic by 2 pi. That's why this property, this symmetry persists at theta equal to pi. Do you agree? Otherwise, if without this periodicity of theta, you cannot see this symmetry. Okay, at theta equal to pi. Is it clear to everyone? Yes, I will write down exactly. Thank you. Yes. Just a note. Yeah. So yeah, due to 2 pi periodicity of theta is equivalent to theta equal to minus pi. Okay? Just to remark that, just write it down. It's super clear for you. Okay. And why is called charge conjugation? Because we have a solenoid with a particle moving. And if you swap the charge, what happened? It reverse, right? Yeah, this is the same action. That's why sometimes we refer to this as charge conjugation symmetry. And to confirm, I will use charge conjugation symmetry, but you should know it is this symmetry. Okay, let's swap Q to minus Q. Is that clear? Say again. Which part? The Lagrangian? Sorry. Probably if you want to see Lagrangian, I will copy it again. Okay, sorry, yeah. Thank you. Yes. Okay. So I will call the corresponding operator is O of C. It's act on O of C e to the IQ, OQ equal to e to the minus IQ, as you said, precisely, okay? With OC square equal to 1. This is why it's a Z2. You square it, and it's back to the identity, okay? This is Z2 symmetry. Now you said, what about how it acts on the state? It's complicated. And this is where the physics start creeping in. At theta to 0 and theta to pi, O of C act on the state differently. Okay? Okay, let's consider the theta equal to 0 because it's easier. Let me, I think I can erase this one. Okay. Okay. For theta equal to 0, okay, we have O of C acting on n, and it changed to minus n. Okay? So from here, if you change n to minus n, what happened? There is a unique ground state from this one, okay? You can even see from the graph. There's a at theta equal to 0. What's the ground state? There's a unique ground state, right? That one. It's a unique ground state, which I call this one, right? And so what happened? 0 mapped to 0. You agree? And so, okay, the charge conjugation. Can I abbreviate when I write because it's long? So CC, you know, charge conjugation symmetry is unbroken. Okay. All excited state N comes in degenerate pairs. Degenerate means they have the same eigenvalue, okay? The same energy. So degenerate pairs plus minus n, you agree? Related by the charge conjugation symmetry. So did you see the pair here in the graph? The intersection between n to minus 1 and n equal to 1 there. That's a manifestation of that, okay? And they're related by charge conjugation symmetry, okay? Because swap n to minus n. Okay. Since now you can combine O of C, O of alpha, O of C act on n. Okay, what do you do? Can you compute this? This make it to minus n. You can use this one with a minus sign and you put it back with a sign. So if you do this, you get e to the minus I alpha n and n. Okay? What does this imply? It implies that O C O alpha O C is O minus alpha. I put this in a box because I will ask you, what is this symmetry? You're telling me, yes, there is Z2. Yes, there is another Z2, but now it formed this algebra. What is this algebra? One is rotation, one is reflection. O2, exactly, thank you. So the shift symmetry combined with charge conjugation symmetry to form an O2 symmetry. Okay, so okay, let me put it here. O alpha combined with Z2 symmetry, or C, to form an O2 global symmetry. Yes, and indeed, you see that OC and O alpha do not commute, right? Because if you multiply OC here, you get O minus alpha OC, right? So since they do not commute, O2, well, this is a mathematical statement, some of you know. O2 is not a direct product, but it's a semi-direct product, okay? That people write it as Z2, semi-direct product with SO2, okay? So Z2 come from charge conjugation, SO2 come from the shift symmetry, but they do not commute. Okay, So at theta equal to 0, there is an O2 symmetry, which I show it in front of you. You can ask, what about theta equal to pi? The story is very similar, but I would like you to pay attention. Because at theta equal to pi, when you put theta equal to 0, your ground state is here. You agree? This is what we're discussing so far. Theta equal to pi, your state is here. Your ground state is here. Ground state means the lowest, the state with the lowest energy, which is here. Now it's subject to crossing. So there's something called degenerate ground state. You see it even from the graph here, okay? Let me write it in sentences. Okay. O alpha act on them as O alpha goes 0 equal to 0, and O alpha act on 1 as a phase. I don't know. I don't have left that. I erased it. But you remember, this is how it acts. It acts with a I alpha n times n. So this is 1. Okay? So they act on them differently. This is different from case of theta equal to 0. You remember? They act on them in the same way. Is that, first of all, this is clear? Okay. In particular, okay. At theta equal to pi, the action OC on the states is O of C act on N, it acts like this. Okay? Is it clear? Now, what's the consequence? In particular, O of C act on 0, it become 1. O of C act on 1, it become 0. So you have two degenerate ground state. OC is a symmetry in your theory, but it's swapped to ground state. Have you ever seen something like this in quantum field theory? Yes, there's something similar to that. But this means that OC is not invariant in each vacua, right? Because if you in ground state 0, this turn into 1. So it's not invariant in the ground state, but it's a symmetry of the theory. What is this called? Spontaneous symmetry breaking. And you might say, Noppadol, I learned that spontaneous symmetry breaking cannot exist in quantum mechanics. Here it is. And I will show you this is robust, meaning you cannot lift this actually. This is a prime example of the spontaneously breaking. It's a symmetry of the theory, and it's not invariant in the ground state. It swapped the ground state around. Yes, indeed, this is a spontaneously symmetry breaking. So let's continue. Now you have seen something interesting at theta equal to pi. Indeed, I promise to you, and it does. So, okay, let's continue and doing algebra, okay? Let me see what to erase. I want to, maybe it's a time to, okay, let's erase this. We also have O alpha, O of C, act like this. Okay, O C, O alpha, act like this. And now you can combine the two. OC, O alpha, OC become N e to the I alpha N plus alpha N, I alpha, sorry. N. Okay. Okay. Since O alpha act on the state as this one, we have OC, O alpha, OC equal to I alpha, O minus alpha, with I alpha become a phase, time identity. Okay, let me put this in a box. Okay, excellent. Can you compare the two blackboards here? This is for theta equal to 0, and this is for theta equal to pi. What do you see? Extra phase. It's an O2 up to a phase, right? So it's not really O2. Have you seen O2 up to a phase? This is, yes, exactly. This is called projective representation. So whenever you have, okay, so let me write down. It comes in many names, and as in this subject, that's why it's so rich, is that, so let me write it down. Yeah, when you see this kind of thing, mathematically, some people call this up to a phase projective representation, because it's not really a representation where you can realize within O2. You have to go to something called double cover. I don't know, have you seen this kind of thing? How many of you seen SU2 versus SO3? Okay. Okay. SU2, what's the smallest representation of SU2? How many dimension? 2. This is called fundamental representation. In physics language, sometimes we call it doublet, right? Okay. Can it be realized in SO3? Not really, because smallest representation of SO3 is 3, it's called vector representation. But it's kind of isomorphic in a way, right? As an algebra. So this is the phenomenon of double cover. You cannot realize certain representation. But some people usually say that, okay, the dimension 2 representation can be projectively realized in SO3. This is the word. So it tells you that O2 is not enough. You have to go to the double cover. And I will show you in a second. This is a universal cover. You will see. 1 second, I will show you. It's a central extension. Yeah. Okay. If you want, we can have a 5-minute break and we can come back because I want to have a 5-minute break every 1 hour. So it's better for concentration and yeah. So, okay. Okay, I would continue. Yep. Any question? I'm very welcome during the break or Q&A session. As I said, I thank you for so much for the question. I think this is really important that the lecture is also interactive. It's not just I speak to you only on one side, okay? More fun that way. Okay, I just wrote what I said in sentence in writing now that the group generated by O alpha and OC is not quite O2. It's up to a phase given by this I alpha. And this I alpha has a name. It's called central extension. Okay, there is a specific name for you. I don't know some of you, I'm sure that there is a group theory connoisseur. And the word central has a meaning. Do you know what center element of the group? Is something that commute with the others, right? Yes, we call the I alpha central because I alpha is central because it commute with O alpha and OC. Okay. Yes, this is equal sign, okay? Yeah, you can compare the two. This is really the central extension. It's just something that appear in the front. Okay. Another perspective is that you can also say treat this and kind of ignore this and say it's very similar to O2. This is mathematically is realized that okay, let me write it in words. By the way, many of these you can learn from book or even kind of Wikipedia already have some good stuff in it. Maybe you can take a look. So if you're not familiar with this. Okay. Mathematically. Projectively. Projectively mean up to a phase, okay? Now, you might say, Noppadol, I will be very clever. I will absorb I alpha into my O and get rid of your phase totally. Can I do that? I will redefine my O such that I absorb the I inside. So now the I is not there. It's a trick, right? Can we do that? Okay, let's try. We could consider V alpha equal to I minus alpha over 2 O alpha and obtain, watch this trick carefully, O of C, V of alpha, O of C equal to V minus alpha. You agree with me? With this trick, you could get rid of I totally. And now you call the O alpha V alpha. It's equivalent, right? And now you can say, now your face disappear. While you are talking about it, I make it disappear in front of your eye. Be careful. You introduce something here. this will make you pay a price. First of all, how do you realize I pi? It now become 2 pi, right? So, okay. You have to, with this trick, you have to extend your range of alpha. Otherwise, you cannot cover the whole thing that is you discussed in the past. So we could consider, but with alpha inside 0, 4 pi, and obtain. We now no longer have I alpha, okay? But we identify V2 pi as I pi, I minus pi, or 2 pi, which is minus 1. Do you agree with this statement? Suppose that you don't extend this range, you cannot have the minus 1 element, which is here, from I equal to I pi, right? Because if you declare that 2 pi is trivial, this will not cover this I pi. You agree? I pi has to be there because it's there. It was there. When you change the variable, it has to be there also. It has to be realized. Because this minus 1 also act on your Hilbert space. You cannot remove it. Even you try to absorb it into here, you have to declare that your new definition contains the same element. This is a crucial point. So it forces you to extend the range twice. And now 4 pi, now alpha here is periodic by 4 pi. Am I too fast here? Okay. And by extend this range to double it, this is called double cover. You extend the range twice, okay? And this is the new central element, okay? So let me write it down. So this is the price you pay by getting rid of this phase, okay? In this way, we get a double cover of O2, also known as pin 2. Okay? Which can be viewed as a central extension of O2 by V2 pi equal to minus 1. So this is a very important part because you can see here the difference between O2 and this projective, this central extension is that minus 1 cannot be realized. I equal to pi cannot be realized by that equation. You agree? There is no phase. So if you put a minus sign, it's not an O2 group anymore. And now it has to be realized somewhere here. And this is V equal to 2 pi, which is turned out to be I to the minus pi, which is I to the pi and is minus 1. Is that clear or is it too fast? Okay. So this type of group that is not quite fit in a way, and there's some element that you cannot use the O2 symmetry to realize it, this is one manifestation of Hooft anomaly. You might say, but this is not definition that you give. Indeed, it is another view of the Hooft anomaly. So let me write it down. In quantum mechanics, Hooft anomaly appear in this way. The central extension V2 pi, which act non-trivially on the Hilbert space, can be realized by pin 2 representation, but not by O2. Okay? This implies that the symmetry group is really pin 2, not O2. Okay? Let me finish the sentence. The inability to realize O2 on the Hilbert space is a way to say that O2 has a Hooft anomaly. So there is an element -1 that you cannot realize on the Hilbert space if you are using O2. This means that it has an Hooft anomaly. Is there any Dutch person here? Could you teach me? This is apostrophe T. It's et. It's et, right? So you should use an in the front, right? And et tooth. Perfect. Please. Yes, it's larger. It's for quantum mechanics, yes. Please. This is a universal cover, yes. It's a general, yes. Yep. So this is one way to see. We will go back to definition that I gave you in probably 10, 20 minutes. Because Hooft anomaly, you can see it many ways. This is one way to see it, meaning that you see it by the fact that the group is not sufficient to there is some operator that act non-trivially on the Hilbert space and the group cannot realize it. Okay? This is one way to see it. And some people even go further. We will see this, that since O2 is generated by generated by O alpha and OC. We also say that there is a mixed Hooft anomaly between Z2 charge conjugation and SO2 shift symmetry. Okay, this is a statement. But pin 2 would not act faithfully on the theta equal to 0. Yeah. This is very important to talk about strictly the form of the group strictly. And some people call this global form and this kind of thing, but this one manifestation that you have to be strict. What are you talking about? Okay, anomalies always belong to this kind of argument. You will see in Mekareeya's lecture that he will really he will go over this thing in more powerful form. Actually, this is a baby form of the. So you have to be strict. Yeah, it's sorry. Now go back to your question. Thank you. People were not so strict about SU2 versus SO3. You might know this in the literature. Sometime you might ask, is it really SU2 or is it really SO3? Right? This is same type of question. When you go to talk about anomaly on the projective realization or this kind of thing, you have to be very strict about which group you are talking about. Whether it's act faithfully mean that is there something that it realized or cannot be realized or this kind of thing. Okay. Yeah. Yes, exactly. Okay. Now let me couple. I have introduced to you at the beginning of the class about background field. Now I will do background field. So you have seen you have seen Hooft anomaly by looking at operator. Now I will use Lagrangian formalism, the action formalism, to show you how to detect this anomaly. Okay. This is method number 1. Now method number 2, background field. Okay. Okay, we turn on a background gauge field. I will write it as A tor D tor. I apologize for you. I'm really weak when it comes to differential form. Weak means I love it. So I will keep using it. But sometimes I know that it's not the best way of introducing it. So I will, for example, yeah, this kind of thing is, I will tell you when I use it, okay? And it's good for you to know both of them because I'm sure that Mekareeya will use extensively differential form. So better get used to it now, but I will be gentle whenever they can put epsilon tensor, I will put epsilon tensor. Okay, otherwise I will, sometimes I put wedge and, okay, but I try to. But I love differential form because it make everything look compact and nice and yeah. Okay, turn on, okay. For the U1 shift symmetry, Q goes to Q plus alpha. Okay, Again, let me emphasize, by background field is that when you compute when you compute partition function, you never part integrate over A. Okay, leave this as a background, meaning that you couple it from the external field. Okay, and now what do? S equal to dTOR 1/2 m q dot. Bear with me, I will write this for you. Theta over 2 pi q dot minus a dot minus ki theta. Okay. Okay. First of all, you might ask, at this point, what are we doing? Why are you writing this? Okay. First of all, observe that if you set a dot to 0, you go back to the same action as before. This we have to agree. If not, then I'm doing something wrong. Okay? Good. So meaning that you can turn on or turn off this kind of thing at will. Right? Okay, let's turn it on. Okay, let's look at this thing one by one. So you might say, no matter why you couple it this way. This is something you are really familiar with, actually. Especially for those of you who study gauge field, coupling to whatever, fermion, and you remember that you have to, teacher will tell you write derivative and replace it by the big derivative. And this is called covariant derivative. This is covariant derivative in quantum mechanics. Why? Because note that the term q dot minus a tau is really when you write it like this, right? Is the covariant derivative. So I'm not doing nothing new. I just couple my kinetic term to the background gauge field in the covariant way. Is this point clear? First of all, it is, right? If you stare at this is really covariant derivative. Now, what is this? Okay, I'm satisfied with these two. Again, this thing you can turn off. If you set a tau to 0, it disappears. If you put it in, you can put it there. You know that this is called counter term. This is the counter term that you see in the first 5 minutes of the lecture. And you might wonder, what you mean by counter term? I have learned counter term in when I compute loop computation. Are you meaning the same thing? Here it is. This is called the counter term. So what do you mean by counter term? Counter term is just a local function of background gauge field. It is, right? K is a constant. I haven't told you what K is. A is a background field. It's a local function of the background field. I can put it on. When I turn on my background field off, you don't see it. In the Lagrangian, you can put this kind of thing, actually. Yes. It has some effect, have some nice effect, which you will see, but you can neglect it. If you neglect it, you don't put this in, it's fine. Nothing will wrong with your system, okay? But you will miss something important. This is just the thing, okay? So let me write it down. Since this counter term is quite special, it has a name, actually. This is called Chern-Simons term. I said, what? Chern-Simons, I told, in 3 dimension, right? Some of you who is a connoisseur might say, it also exists in 5 dimension. Yes, this is in 0 plus 1 dimension. It look like this. So for those of you who are familiar with differential form, it's in 3 dimension is take the form of A wedge dA, right? This is just the A, basically. And it comes with a coefficient K, which I will tell you. Okay. Trust me, if you don't know this term, don't worry. Just if you don't put it, well, your life will not so miserable, but you will miss some physics. But I will tell you that you can add it in, and it's beneficial for your life in a second. Okay? No, no gauge invariant. You will have to impose this later, but it's not about not putting this term. If you're not putting this term, your Lagrangian, your action is completely gauge invariant. Okay, this is just, well, you can set k to 0, please. I mean, it's annoying me, so okay, that's also fine. Okay, so let's analyze this. Let me write it down first. The term ka tau is known as the Chern-Simons term. It is a counter term since it's a local function of the background gauge field. A. Okay, that's it. Okay, let me talk about Chern-Simons term. How many of you have seen Chern-Simons term in 3 dimensions? Ooh, okay. Do you know a property? Wait a second. This K has a name also. This is called Chern-Simons level, okay? Okay, how many of you knows what the property of Chern-Simons level has to be? Do you know why? And do you know why? Okay. Since not everyone knows, let's get on the same page, okay? The Chern-Simons term is compatible with gauge invariant if K is in Z. And if you know this, the proof is exactly the same as theta. Why is a 2 pi periodic? Because I will consider instanton configuration again, okay? Compactify time direction. Okay, let me provide argument. This is an argument. Again, we compactify time, okay? T goes to T plus beta as usual. And look at the path integral. So with the S, Chern-Simons become, let me write it in full, IK integral d tau a tau, right? This is what we have, okay? In the path integral, what do? We raise it to the e to the minus s, right? This is exponential ik integral tau a tau d tau, okay? And now we look at gauge transformation. A tau goes to a tau plus d lambda over d tau, okay? With lambda tau winds around S1 tau. S1 tau is the time direction that we compactify. Okay? Now again, we do the same trick again and again, that S1 d tau d8 tau over d tau is 2 pi p. We see this p again. This is instanton number. And under gauge transformation, e to the minus s cs transform as e to the 2 pi I k p e to the minus s cs. You agree? Okay, this is invariant. Gauge invariant if k is in Z. Okay. I just show you that Chern-Simons level has to be integer. Okay? Please. Yeah, indeed. It just yeah, exactly. This is the winding. Okay? Good. When it have a non-trivial winding, you cannot deform this back to the identity, meaning that you cannot shrink it to just the identity. It's not connected to identity. Some people call this non-trivial winding of lambda when p is larger than 1. This is called the large gauge transformation. Okay, it means a gauge transformation that cannot be continuously deformed back to identity. So if you haven't heard this term, now you see it. Okay, please. This, it's hard. No, it's not. It's not. This is the only way you see this type of argument. You have to compactify time. And you can do this because it's the same footing as your space, basically, because we are in Euclidean. But I can, as I emphasize again, this beta can be made as large as you want. Yeah, it doesn't matter. Okay. Good. This is a large gauge transformation when P is greater than or equal to 1, because it's non-trivial winding. Yeah. Yeah. These are not the related, these are not at infinity, first of all. These are configuration of the gauge field where I introduce it. Okay, this is a background gauge field. You can make this dynamical if you choose to part integrate it. And if, well, if you put k to be 1/2, this is not consistent because I can find a configuration which destroy your system, basically. It's not gauge invariant, right? So it's not at infinity. This is a symmetry. This is the global symmetry, not at asymptotic. It's in the theory. Okay, please. Ah, thank you. Thank you. Okay, please. K is a constant. Okay. If you even if you put an external electromagnetic field into the system, this K has to be quantized. It's imposed. It's like quantization of magnetic flux, basically. Yeah. It's a strength of that. It has to be in some unit, in some quantized unit. Okay. Otherwise, you violate gauge invariant, and which is a sacred principle. quantum system. Okay. Okay. Are we okay with this? Now let me move on. So this is quite important because I know that in the introductory course you rarely see this kind of doing it with a accessible example. Usually Instanton you do it in 4 dimension is more complicated, but this is in quantum mechanics you can do a lot of calculation more in an easier way. Okay, let me erase this. Okay, now why we bother? Okay, by the way, I can also put this, well, compactify time and so on. So, okay, for non-zero, A of tau, the system with theta is not the same as with theta plus 2 pi. Obviously. Okay, so now what happened? If I put theta and k, now I have 2 parameters in my theory, right? It's not just theta alone, I put k. What happened? Instead, if I shift theta by 2 pi, what happened? There is an a drop out, right? I have to compensate with my k. And you will see that theta plus 2 pi, I have to shift k by -1. Okay. So this is this is almost like a helix. Can you start wheeling it? Because when you go around it, it forces you to decrease this parameter, right? So now you have 2 parameter space. It's not just theta, and it's not a 2 pi periodic, but this k. Now, you see, if I don't put this Chern-Simons counter term, you kind of miss something, right? Okay. The duty of k is to absorb this thing with a 2 pi periodicity. Okay. The charge conjugation, okay, recall. The charge conjugation symmetry acts as q goes to minus q, but now we turn on A. I have to talk about how it acts also, but this must now be accompanied by A tau goes to minus A tau, theta goes to minus theta, and K goes to minus K. You agree? To make the action completely invariant. Now, we can look at two parameter, the parameter at 2 points again, which is theta equal to 0 and theta equal to pi. At theta equal to 0, we can choose k equal to 0, and it is indeed a symmetry of the theory. Okay? Right? If you set theta equal to 0, we can choose k equal to 0, and now you can see that accompanied by this is just a symmetry of the theory. It's clear, right? K you can choose at will. Okay. However, look at this theta equal to pi. There's something. At theta equal to pi, under the charge conjugation symmetry, what do you see? You have theta equal to pi with the k. This goes to theta equal to, remember, theta goes to minus theta, so this is theta to minus pi, and k goes to minus k. But this is equivalent to theta equal to pi with shift k by minus 1. This is what we agree, right? For the theory to agree with each other, you have to match this with this. Do you agree? However, there is no integer solution for k equal to minus k minus 1. Oops, what happened? The charge conjugation symmetry is broken. Is broken upon turning on A for the shift symmetry. Okay. So, okay, let me summarize what we are doing. It's probably too messy for you at this point. You said, I just show you without this A, at theta equal to 0 and theta equal to pi, there is OC and O alpha. These are symmetry of the theory. Now I turn on background field for the shift symmetry, right? This A is for the shift symmetry. And I found that at theta equal to pi, the charge conjugation symmetry is broken. Noppadol, turn it off. Yes, you will restore it. But when you turn it on, it's broken. What does it mean? It means that when you couple a theory to an external background field corresponding to one symmetry, the other symmetry is broken. So these two symmetries talk to each other in some way, right? Otherwise, there would no such an effect. When you turn on background field to one, the other just disappear. This is called mixed Hooft anomaly, meaning that you turn on background field for one symmetry, the other symmetry is broken. Okay? Let me write it down. This is very important. Now you see second way of seeing mixed Hooft anomaly. Yes, you can. You can also. It's just a bit more complicated. I do the one that is simpler. Yes, but you can. Okay, I have to explain to you. I can also do, but it's a background field for the discrete C2 symmetry. Mekareeya, they'll sort of probably do it in the more detail, because the background field for discrete symmetry, you have to require the holonomy to be quite special. But yeah, here I just use Chern-Simons and this kind of to absorb it, so it's kind of simple, but indeed you can. And mixed anomaly, you can always do both, okay? Actually, there's a nice way to see that. I'll show you in a second, okay? So upon turning on background field for the shift symmetry, this implies the mixed Hooft anomaly for between the charge conjugation and the shift symmetry. Okay, so you have seen two ways now. Let me mention the third way. This is called the partition function. Finally, I do something I promise after almost 2 hours. Okay, so let's compute partition function of this theory. and see. Now, this is the most general method of detecting. Okay, so let me emphasize this point. So the lesson here is what? The lesson here is that you wouldn't see this mixed Hooft anomaly unless you turn on background field, right? You can turn it off and you can live comfortably and you might say, these two symmetry exist. If you work hard enough, you might see that, there's a phase that cannot be so this is kind of signal you have seen in the first way. This is second way, you turn on background field, but you have to turn it on to be able to see it. And now suppose that you make this dynamical by part integrate. This symmetry is really broken. It's not just turn it off or turn it on anymore, because when you make the field dynamical, you cannot turn it off because you part integrate. It's not, you cannot choose the value as you will, right? It's there, it's dynamical. So here, the lesson is that you have to turn on the right background to detect this kind of subtlety in the system. This is the art of it. And if you don't turn it on, you miss it. Okay? Exactly. Yeah, then you violate gauge invariant. So yeah, this is also a character of Hooft anomaly. You cannot remove it by just redefine things. This is crucial. You can, if anomaly can be removed by just field redefinition, I wouldn't be here telling you this by now 2 hours, right? Yeah, it's just trivial. But here, no, because if you try to absorb it, it becomes another animal. This is the character of the Hooft anomaly. And now we see in third way, which is really what you said actually in the logic that you said. Okay, again, we compactify the Euclidean time. Tau goes to tau plus beta, and you compute partition function. This you probably familiar. I mu q. Okay, so let me define notation here. The beta is the same as beta here, okay? When you compactify Euclidean time, you can treat it almost like a temperature, as you know, in the partition function. Q is the shift U1 charge of the state. And mu is the conjugate chemical potential. How do you define mu? You define mu as let me and mu I define it as integral of S1 d tau a tau. Okay. Well, and as before, now you can repeat the same statement. requires that mu is equivalent to mu plus 2 pi. I don't have to repeat this, right? You can see it from, it's the same integral as before, okay? Okay, now we take theta equal to pi and compute partition function. Okay, so we focus on ground state. The ground states, which is 0 and 1. And I normalize this E to be 0 because we are in the ground state, okay? And neglect contribution from excited state for now, okay? Okay, under the U1 shift symmetry, 0 and 1 carry charge. How much? 0 and 1, right? Because it's act like, you remember, e to the I alpha n for state n. The charge is what you read in the exponential, right? Yeah. Carry charge 0 and 1 respectively. Okay. So what's the partition function? Z as a function of mu. It's just e to the I mu times 0 plus e to the I times mu times 1. This is 1 plus e to the I mu. Okay? You agree? Is this charge conjugation symmetric? No. Why? Please take a look at this. Under charge conjugation symmetry, A tau goes to minus A tau. Therefore, mu has to go to minus mu. And is this C minus mu? Is not C of mu. So it's not charge conjugation symmetric. Indeed, when you turn on chemical potential, you can see explicitly also that partition function does not have conjugation symmetry. Let me erase this. Well, in fact, we even have C of mu, C of minus mu equal to e to the minus I mu Z of mu. Okay? So turning on the chemical potential for the shift symmetry breaks the charge conjugation symmetry. And this is the mixed anomaly. Okay? Again, same phenomenon. Now, here, you can absorb, with this, you can absorb it. Or not absorb, but okay. E to the minus mu, I mu, can be reproduced by e to the minus delta S Chern-Simons, right? With delta Chern-Simons, with delta, let me put it like this, delta S with delta S equal to I mu equal to I. You agree? This phase you can add to the action, this term. And when you raise it to the exponential, you reproduce this phase. Okay, so this is the app, the thing that tells you that you should add counter term to reproduce this phase. Okay, this is the K that I talk about, and this is answers some of your question that say, how do I know when to add the counter term or not? Here, okay, with this is which where Chern-Simons level is -1. Okay, good. Now, suppose that I want to restore the charge conjugation symmetry. So meaning that I have to put z of minus equal to z of minus mu equal to z of mu. Okay, so let's do that. Okay, I can erase this. Okay, so this is 1 hour. You want to take a break? 5 minutes? Yeah, okay, and then we can come back, okay? Yep. Sure, sure, sure. Yep. Yet. So in differential language, the Chern-Simons term is a dA simply. Yeah, this just a tau. It has one component. It's a time component. Okay, so the action part is integral dA. Yeah, yeah. So when I do the gauge transformation, I get a plus d mu d alpha. Yeah. But then so this yeah, yeah. But it is always zero. No, because, okay, where were we? Let me, otherwise, yes, you can, this is when you write it in the form, it's reduced by Stokes theorem, and this is Stokes theorem. Yeah, it's not exact form, because it's a one. Yeah, this is something for, I don't know, which stress. It's not exact thing, it's analogy. You sandwich and then, then becomes trace and sum over it. Yeah, no, but it's the same. It's the sum over n of the blah blah blah, and you can write it as n sandwich n with the action in the middle, with the bottom as a factor in the middle, and that's a trace. You get what I'm saying? Like to change the a consistent break. Yes, look, this is simpler. You see it, this is Hooft here with 2 and then further point.
here for fun. We are here for fun.
B2 pi is exactly this one.
No, but this is perfectly fine. I was asking if there was like an interpretation in terms of
Projective representation.
yeah, of representation of the fundamental group. So this extension, you have many because you have I alpha. Yes. You have to add which alpha.
Yes.
While for SU2, you just need to add minus 1.
This is actually right.
But here no, you have the e to the I alpha for each alpha.
You should look at half of it. This is the real central extension. So this is minus 1. So
this
the
is
central extension,
alpha.
yeah. No, this value for any alpha, because all 2 is a continuous group.
Exactly. But then, you don't have just to add 1, you need to add 1 for each alpha.
Yes.
It's different.
But this one is projected.
So I think then the number of elements is the contact interval of the diagonal.
Exactly, yes.
But then everyone is discrete.
Exactly.
So the element of the extension are bounded by the contact interval.
By computation of partition function, you should compute by time, otherwise you get that. Yes, you should. You should, in order to see this quantization. But you are allowed.
So if I don't,
you cannot see it's the same.
Is it straightforward to, that Z up there,
Yeah.
is that the same as the normal path integral with the exponential minus S?
Yes.
Right.
Exactly.
Is it easy? Is it difficult
Yes.
to show that
It's
it's the same?
well, okay. I have a discrete level.
Yeah.
So
So you're summing over the level.
yeah, so it's the sum of the level basically. Yeah.
Okay.
Yeah.
And the minus beta E is
Yeah.
just e to the minus
Exactly.
S. Okay.
And I focus on the low lying states.
Yeah.
If you take it to those excited states, you have to sum all of them.
Now how do you get from the beta E form? So that's equal to exponential minus S.
The E form, yeah, the
Okay.
E one, yeah, it's hidden there.
Right.
Yeah.
How do you show that? That they're the same?
So basically, action in Euclidean, this is the trick. When
Okay.
you in Euclidean, the action and energy
Yeah.
is the same.
Oh, okay.
Yeah,
Right.
it's the stable configuration.
Right. Okay. Right. So it's
That's why I prefer to do Euclidean from the beginning.
right. So
It has a price for you. When you turn into the quantum field theory, be careful with some time.
right.
Yeah, but for now it's okay.
So can you do the same expression in a quantum field theory?
I will. I will. But the spectrum is not so distant. But you will see some of the element of that. Wait a little bit.
I don't feel too stressed out.
Okay. Shall we start again? Okay. So again, we try to do the same trick again and again, and now my attempt is to restore the charge conjugation symmetry. And I said I write down my new partition function, call it z tilde, as e to the minus I mu over 2 plus e to the I mu over 2. And now you see that it satisfies this property. Now let's look at which price we pay. Okay? So now you can rewrite this as this. You agree? Okay. So now the phase. Here, the phase can be reproduced by e delta e to the minus delta s with delta s equal to I mu over 2. Now it's equal to I over 2 dA tau A, which is mean Chern-Simons level equal to minus 1/2. Oops, you violate gauge invariant, right? This is number one. You already see here that you have to violate something if you want to restore something. This is an anomaly. You move it around, it reappears somewhere. You cannot remove it totally. Okay, suppose that we continue by neglecting this point. Let me erase this maybe. Okay, so this violate gauge invariant. Okay, let's look at this interpretation of this equation. Okay. We assign charges Q equal to plus or minus 1/2 to the ground state. 0 and 1. You agree? Because in the definition of partition function, this Q is what multiply I mu, right? So this, what we are doing is here. Well, okay, now let's map to the double cover that this half charge half integral charges are not allowed by O2, but they are allowed by pin 2. Again, this is the trick of going to double cover. It's like SO2 and SU2 and SO3 that I mentioned. The two-dimensional representation, which is smaller, right, is allowed by SU2, but it's not allowed by SO3. This is exactly the same phenomenon. Okay? So you have to go to double cover to be able to allow this charge. This is another manifestation. Now I'm trying to map back to the method number 1. Okay? This is in agreement with central extension. Okay. And also implies that O2 has a top anomaly. Okay? Good. Now, you said, okay, so we lose it totally. This is the manifestation. Another manifestation of a top anomaly is that you can cancel it. Can you? Okay, I told you that if you move around, it reappears somewhere. Indeed, it does, right? And there's so many manifestations, at least 3 by now. Now I will tell you the point of view number 4. This is called anomaly inflow. Okay. Let me erase this. Okay, that phase is important. I will keep it. So the way to realize this anomaly or cancel this anomaly in a consistent way, which can be applied to any top anomaly, is to use the something called inflow process. Okay. To cancel the anomaly, what we're doing is that we look at our one-dimensional system as a boundary of a two-dimensional bulk. Let's call the two-dimensional bulk support on a manifold M2. In this way, you can cancel anomaly. So I will tell you how, okay? So you attach your system to a larger system. Now it has a two-dimensional. So your quantum mechanics lives here, okay? This is your roll line, basically, and this kind of thing, and then you attach the bulk to it, okay? At this point, it's okay. Now, the next part is now your theory has a Q coordinate and so on. So what do you need to extend to the bulk to make it non-trivial? You have to take this gauge field, this A that you were just dealing with, but you have to extend it to the bulk, okay? So gauge field that used to be one-dimensional gauge field, the A tall, now you have to say it has another component that extend to the bulk. Is that clear? This is the process, okay? So pick a two manifold M2 that ends on the whirl line of our quantum system. our quantum mechanics, we extend A to the bulk. Now, next question, how do you extend it? So suppose I'm observer here. What should A be a function of? The answer is, doesn't matter. This arbitrariness will just cancel ambiguity that you had in your quantum mechanical system. So let me demonstrate. So you remember there was a phase which you cannot resolve. This is the e to the minus I mu over 2. This is inconsistent, right? Because first of all, mu has to have a periodic over 2 pi, and this is not, right? When you shift the mu by 2 pi, this is not consistent, right? So how do you realize this? So basically, let me write it down. The half Chern-Simons level, okay, the half Chern-Simons level, half, half integer Chern-Simons term ds equal to 1/2 integral d tau a tau is not consistent in 1D, but it can be cancelled by the bulk action I over 2 integral f, this is differential form, with f equal to dA. So now I'm in 2 dimension. This A, I have to extend it. This f is in 2 dimension. I integrate over it, right? This is a consistent action in 2 dimension. I can use this to cancel this inconsistency. By what? Simply Stokes' theorem. Okay, so using Stokes' theorem, Stokes' theorem, we obtain I minus over 2 integral of boundary of M2 d tau a tau. This, I forgot an I, sorry. Okay, this cancel precisely. Can you see this? This and this cancel precisely. This is consistent in 2 dimension. It's just a topological term in 2 dimension, okay? So you can write this thing and you use this to cancel the anomaly in the on the boundary. So if your boundary theory has anomaly, what you can do is that you can attach to the bulk and then put the appropriate term in the bulk. This, I don't know, I have no prescription to tell you, this depends on from theory to theory. You can put it in and then use a variation and then you see that it cancels. This mechanism is called anomaly inflow, okay? Yes, I have to yes, exactly. It is, but it's guaranteed. This ball action, yes, so anomaly can be cancelled by attaching into bulk. And the bulk is that it doesn't, the ambiguity of the anomaly was absorbed by the ambiguity of the extension that you of the gauge field to the bulk. But once you choose it, it doesn't matter. It will cancel. And when the combined system is free of anomaly. So let me summarize. No, it doesn't matter. As long as the boundary is your system is fine. It's it's not a. It's locally, yes. Yeah, it has a bound. It's a manifold with boundary. You have to be careful. It's not a closed manifold in that sense. Yeah. So the conclusion is that the charge conjugation symmetry can be restored by coupling the system to the 2D bulk. Okay, this is how to deal with the anomaly. Okay, to top the anomaly. It's always possible this way. This theory has a name in the literature, many names. Some people call anomaly theory. Some people call SPT phase, symmetry protected topological phase. Some people call it non-invertible field theory. The reason is called non-invertible because this is the action. When you write it in the exponential, it's a phase. So it's invertible in that sense. Okay? I think Mekareeya did this in much more detail than me. But every topic that I will show you in this lecture, I will write bulk theory and how to show it that it's always can be cancelled this way. So let me conclude before going to the most robust part that okay, you might say that this look very trivial. What you're doing is just Stokes theorem. Yes, in this example, but I guarantee that when it's more complicated, this action will look more complicated. Okay, please. Yes, because you use do you use the theory on the bulk to flow? Yes, to cancel the anomaly on the boundary. This is the flow in this sense. Please. Yes. Yes. Yeah. I don't know a single one that cannot be done by. There is, yes. Yeah. Yeah, exactly. But if it's an integer phase, you can just remove it by counter term. But symmetries remain broken. Okay? This restore the symmetry for you. Okay? Even with the background field. Yes, I will show you. 1 second. When I do ABJ anomaly, I will write down that term for you. Yes, it's precisely that. And if it deserve a name, West-Sumino Witten, it's probably something non-trivial, right? Yes, indeed. I will write that term. Just wait a second. Yeah. Okay, so conclusion. Yes, this is the baby version of that. Yeah, indeed. So at theta equal to pi, O2 is projectively realized, and the vacuum we have seen breaks it spontaneously. O2 symmetry is centrally extended to pin 2. And if we couple the system to a U1, which is in this O2 background field. Um, for the shift symmetry. The charge conjugation symmetry is broken, is necessarily broken. This can be avoided by coupling to the 2D bulk. So that's the idea so far that we are talking in this lecture, okay, in these hours. So I spent a lot of time doing all of this in detail, but I hope you get some feeling now about top anomaly. There is something that I really would like to stress, and this is something that I think it's really important, is the dynamics of this. So far you might say, Noppadol, you just write down a free system and you declare that your system has anomaly. What's interesting about it? Where's the interaction? Right? I just do free theory. I just look at the particle goes around the solenoid, no potential, no whatsoever. How powerful this is, you might ask. Rightly so, indeed. But you know that anomaly is robust. It's a really robust object against certain class of interaction. And I will show you now how to use this thing. And this is extremely powerful. That's make anomaly even such a rich and beautiful object. You have already seen 4 point of view of anomaly. But now you will see that it's robust against interaction. So let me turn on interaction in the Lagrangian that we just studied. Of course, not any of them, because if the interaction remove the symmetry totally, there's no point to talk about anomaly, right? But if a Lagrangian still left some symmetry, have some symmetry left under that, you can still use this thing to nail down the ground state, the property of the ground state, and so on. Okay. Good. So let's look at this Lagrangian. We modify it a little bit. Now I put this term, cos 2 theta. Okay, so, and I put lambda. This is the coupling of my interaction. You will see that I will never have to talk about this lambda ever again. And you can send it to near infinity or whatever. My physics will not change, okay, because of the anomaly. And this is nice. Because you might say, in the strongly coupled system, which is very hard to solve, as you know, how does a system behave? And I can use this to constrain the theory, okay? So this has two classical ground state. Q equal to 0 and Q equal to pi. You solve this by taking derivative of this, okay? This is a classical ground state. The U1 shift symmetry is explicitly broken to Z2. At theta equal to 0 and pi, we have 2 C2 discrete symmetry. Which is O of pi. Now there's no alpha anymore because you cannot shift it by any angle. Is not allowed by this term, okay? There is O of pi, which is shift Q by pi, and O of C, which is the charge conjugation as usual. And this is a symmetry at theta equals to 0 and pi, okay? And we have seen, as previously, at theta equal to 0, we have O pi, OC. This you have seen, okay? Just look at the note, okay? So they commute. So what's the symmetry here? Z2 times C2. Okay. And you will know by now that the interesting part was at theta equal to pi. As before, OC, O pi, OC equal to minus O pi, or if I write this, I can write this down. Now they do not commute, they anti-commute. Okay? Who can tell me what this group is? Let me write this down. Define R equal to O pi OC and S equal to O pi. Obviously, S square is equal to 1. R square is equal to O pi OC, O pi OC equal to, I work it out for you, this is minus 1. So meaning that R to the 4 is 1. Could you tell me what this group is? Dihedral. Exactly. Now you see that turning on this, okay, let me recall. Before turning on this interaction term, the potential term, at theta equal to 0, you have O2. Now it's explicitly broken to Z2 times C2. And the pin 2 become what? This weird group. This is called dihedral group, okay? This is the R and S generate the dihedral group. I call it D8, okay, of order 8. Just to be careful, in the literature, there are two nomenclatures. Some people who use D4, some people use D8. I use D8, okay, of order 8, sorry. This is a symmetry group of a square, okay? So again, you see all the statement that what we have done, now you can see even clearer that we don't have to deal with pin 2 anymore. If you're not familiar with pin 2, look at this example. It's D8 in front of your face, right? Yeah. So, well, again, this is the most important part. The central extension and the Hooft anomaly central extension means is extended to D8. And Hooft anomaly, I mean C2, a Hooft anomaly of Z2 times C2 as usual, okay? means that the system must have a non-unique ground state. This is the most important thing that you see in this lecture. I turn on interaction. How do you know that the two ground state that I talk about was still there? It should be wiped out totally by interaction. It's not. It's there. Why? I will give you argument now. Suppose, on the contrary, we prove by contradiction, okay? Contrary, that we have the ground state is unique. If the ground state is unique, it is how many dimension? The Hilbert space must be one-dimensional. So this means that OC and O pi acts as a phase. As phases. You agree? Because one-dimensional, it cannot be more. It cannot be matrix. It has to be one by one matrix, which is a phase. Okay? In contradiction, contradict the anti-commutation relation. If it acts as a phase, it cannot produce a minus sign. Right? There you go. So I have shown you that even I tune my interaction to be very strong, the system must have a degenerate ground state. Full stop. This is anomaly. Why is anomaly? Because it's a central extension, and this implies the Hooft anomaly of Z2 times Z2. It's really strong. Okay? At least all of this type, you can argue even for the other type of the potential. Square, polynomial of cosine 2 theta, or even 2nq. You can generalize all of these things in lots of possible way. The argument is still there, okay? Now, okay, so we contradict it, so we show this statement. So the conclusion is that even if we add the interaction, and it doesn't matter what the coupling is, okay? The theory is still, okay, the theory has a exactly twofold degeneracy. This is consistent with the fact that Z2 times Z2 is broken to Z2, is spontaneously broken to Z2, okay? This first of all. And look at this. This argument is beautiful. It has something hiding inside here, in the sense that, so I analyze for you the Hooft anomaly using algebra and so on, okay? And I use the argument to argue about ground state of the theory. This is what is called Hooft anomaly matching. Okay, you have heard this for first time. This is a most important one of the most important implications of anomaly. Okay, this type of argument is called Hooft anomaly matching. Matching between what? I analyze it using operator, and I use it to deduce the ground state property. Okay. In quantum field theory, you can work this out using Lagrangian. There is anomaly. And you conclude that in the low energy effective field theory, there must be something non-trivial living in the infrared or at the long distance. If you more condensed matter. This type of argument is called Hooft anomaly matching, okay? Usually the existence of anomaly implies that your system must have something non-trivial. This is one of the examples. And it's robust against interaction. What interaction I use is to just look at the what symmetry is still remaining, okay? I haven't even touched the coupling part. It doesn't matter. So this is a very solid statement, and you will see the power of this again and again and again in the next lecture. Okay, so I think the time is it running out now, or it's 1 hour? Now, yes, okay, it's lunchtime. Okay, I'll take question, please. Spontaneously, you mean? No, if it's, okay, exactly. This is very robust in the sense that the ground state always degenerate, right? If it degenerate, you have to explain this using symmetry. This is, okay, let me emphasize. In quantum mechanics, usually you learn that, when you have a degenerate ground state, there's some symmetry, okay? And usually perturbation lifted and this kind of thing. No, this is robust, okay? Against, well, you can, this is not even so small perturbations, okay? So it's robust, and whenever you have a degeneracy of this kind of type of thing, you have to explain it using symmetry. Some symmetry must permute them. And if the symmetry of the theory, of the Lagrangian, of the Hamiltonian is there, and it's permute ground state, the only way you can conclude this is spontaneous symmetry breaking, okay? If there's no more question, I'm here, so you could be welcome to come to ask me any question, and have a good lunch.